All right, now we're going to talk about bounded sequences and monotone sequences. So first of all, bounding. So we've got to say some real value m, some real number m, and you have a situation where an is less than or equal to m at all times for all positive integers n. That means every single input you have, then it's bounded above by m. And similarly, if you've got a value that's always below or always less than or equal to the sequence value, then it's bounded below. So I'll put an M1 here, and I'll put M2 here. And if our sequence looks something like this, and it goes on forever and makes kind of a sine or cosine pattern, something along those lines, you're going to have a bound. Now we can, given where I've written this, we can shrink those, to be up here and down here, something like that. But at any rate, it appears to be bounded above by M1 and bounded below by M2, although we can figure out a number that's more in line with here, and we can make our end there instead. Although, it can be bounded, if it's bounded by 100, it's going to be bounded by 200. If it's bounded above by 100, it'll be bounded above by 200 as well. So as long as that value is always above every value in the sequence, then you've got no issue. Theorem 5.5. This is a very short but very important theorem. It says if sequence AN converges, then it's bounded. So if it converges to something, that means it's not going off to infinity. It's going to be bounded. All right, it's not going off to infinity or negative infinity. So that's very, very cool, because if you just find that it converges, you say, well, yeah, it's bounded. Actually, last bit here, a bounded sequence is one that's both bounded above and bounded below. So if you've got some value that is below it, that's going to be a hard floor, and above it's going to be a hard ceiling. You've got a bounded sequence. Okay, so let's talk about something that's increasing. You're increasing, and you've certainly seen something like this in algebra, certainly calculus. If for each subsequent value, so if you're looking at an, it has to be less than or equal to an plus 1 for all n greater than whatever your existing n is, or your initial n is, then it's increasing. So that means it's always going up or staying the same, never goes down. Similarly, the sequence is decreasing if your lower, so an is always bigger than an plus 1, so or equal to. So it's going down in that case. And a sequence is a monotone sequence for all n greater than some n naught if it is increasing for all n greater than n naught or decreasing. So a monotone sequence means you're always doing that. So we'll do an example of these in a bit, or at least to determine one. And then finally, theorem 5.6, a monotone convergence theorem. If an is a bounded sequence and there exists some positive integer n naught such that your sequence is monotone for all values above that. So consider your n sub 0 similar to like your capital N in the previous ones. We're going to pick a spot on the sequence, and it's going to work for everything after that. So you can have a sequence doing something crazy in the beginning, say going way up and going way down, and then eventually tapering off. So that's kind of what the feeling is here. But anyway, if it's monotone for all values above your chosen n, then your sequence converges. See if we can try to put this to use with this homework problem. This is problem number 32 from 5.1. The instructions say for each of the following sequences whose nth terms are indicated, state whether the sequence is bounded and whether it's eventually monotone, increasing, or decreasing. All right, well, let's take a look here. What happens for our first value? So if we take A1, that's going to equal natural log of 1 plus 1 over 1, which is ln of 2. Okay, that's not a problem. What about A2? Well, natural log of 1 plus 1 over 2, which is ln of 3 halves. Okay, well, that's a little bit smaller. That's, sorry, not A, I want A3, excuse me. A3 is this, so that comes out to a 3, so 4/3, ln of 4/3. A4, that'd be 4/4, so we're looking at ln of 5/4, and so forth. So all the way down to an is that ln of 1 plus 1 over n. Well, what's happening? What's happening here? So we're starting our the natural log is a graph that looks like this. And that point is 1, 0. That's where a point is here. So ln of 2, you're saying, so then 2, ln of 2 is here, ln of 3 halves is over here, ln of 4/3 is there, and so forth. So that's kind of the range of where you're at. So what's happening? Each individual one after it is getting smaller. So we have very simply that it's going to be monotone decreasing. I guess this is monotone decreasing. It's always going down. ln of 2 is larger than ln of 3 halves, which is larger than ln of 4/3, and so forth. That's why we have this. So is it bounded? Well, the highest value you can reach is ln of 2. So bounded above. That's as big as it can get. Well, what about as small as it can get? We could just, we put in a million. It's going to be ln of 1 plus 1 over a million, which is very, very close to ln of 1. Well, what's ln of 1? It's 0. So we can't actually get to 0, but that's a bound. So this is bounded below by 0, which is ln of 1.